All right, welcome everyone to our presentation Wash Your Phone, where we introduce novel USB-based file access attacks on mobile devices. My name is Florian Draschbacher. I'm a PhD student at Graz University of Technology, where in my research I deal with various aspects of mobile security.
Hello, also from my side. My name is Lukas Ma. I'm a PhD candidate of Graz University of Technology. My research area is system security, in particular kernel and side channel security. Over the last 2 decades, mobile devices have grown into important everyday companions. As a result, they commonly contain a lot of sensitive user data, such as pictures, messages, and login credentials. This amount of data stored on mobile devices has made them interesting targets for attackers. One of the primary entry points for attackers can be found in the USB interface of mobile devices. In this presentation, we show novel USB-based attacks for 2 different scenarios. In the first scenario, the attack is carried out from a malicious phone charger. Here, a user confirmation prompt normally ensures that the user is aware of data extraction. In the second scenario, the attacker has physical access to a device which is locked. This lock screen normally prevents access to the data stored on a phone. We have assembled history of USB-based attacks on mobile devices running iOS and Android. On the left, you can see attacks that operate as malicious USB devices. This is consistent with the malicious charger scenario described on the previous slide. These attacks exploit high-level design flaws in the trust model of mobile operating systems. The first attack in this category, the famous ChoiceJacking attack, used malicious chargers that acted as a USB host. This allows them to extract data over protocol such as the Media Transfer Protocol, or short MTP. ChoiceJacking and related attacks were quickly mitigated in both iOS and Android by introducing user confirmation prompts that are shown when the device is connected to a USB host. Data access is only possible once the user confirms this prompt. So far, this mitigation was thought to effectively prevent malicious USB charger from secretly acting as USB hosts. Therefore, subsequent attacks acted as USB peripherals where no user confirmation prompt has been added to this day. However, the possibility for malicious peripherals are rather limited. For example, a malicious charger secretly operating as a USB to HDMI interface can only extract information that is visible on the screen. On the right, you can see known attacks that allow data extraction through physical access to a locked mobile device. Generally, these attacks exploit low-level implementation flaws. They are therefore usually more targeted to individual devices and manufacturers. For example, the famous checkmate use of the free vulnerability in a boot ROM allowed compromising iOS devices in the past. These types of attacks are also used in commercial forensics tools such as Celebrate UFED. All these attacks use the USB port as the attack vector. As you can see on the right, every recent mobile device is equipped with a USB Type-C connector, which serves multiple duties. It is used for transmitting both data and power. And what is interesting about USB-C ports is that both power and data are bi-directional. This means that the port allows charging the mobile device as well as supplying power to attached peripherals. It also means that the device can act as either a USB host or USB device. As a USB host, peripherals such as USB keyboards and mice can be attached, while as a USB peripheral, the device can be connected to a computer and act like a USB flash drive itself. The power and data roles are negotiated using a protocol called USB power delivery. This protocol runs over dedicated data lines within the USB Type-C connector. Finally, it's crucial to note that despite the possibility to act either as a USB host or a USB device, a USB board can only assume one of these roles at a given time. We mentioned so far that the user confirmation prompt was added as a mitigation to ChoiceJacking attacks. In other words, a malicious charger that acts as a USB host. Here is how this user confirmation prompt works. First, the mobile device is attached to a USB-C host, such a computer. At this point, the computer will display that an MTP device is connected. However, it will appear as if it contains no files. The user is required to unlock the device and accept the user confirmation prompt first. On the right, you can see examples of how this prompt looks on different Android versions and on iOS. Only after this prompt has been confirmed, the mobile device will expose its files over the MTP connection. All right, the background out of our way, let's talk about the attacks we found for the first scenario, where the attacker operates as a malicious phone charger. When we talk about a malicious phone charger, this is what we actually mean. We assume that an attacker has modified an existing charger, for example, by flashing modified firmware or by exchanging internal electronics. The result is a charger that appears and functions like any other phone charger, but stealthily tries to extract data from any connected device. Malicious charger can be easily deployed at airports, museums, and hotel rooms, where users are used to charging to existing infrastructures. We base our attacks on a conceptual flaw we identified in the user confirmation prompts implementing for mitigating ChoiceJacking. As a recap, this mitigation requires the user to unlock the screen and confirm a prompt before data access is possible. This is intended to ensure that the user intentionally enables USB file access. To ensure that is the legitimate user taking this decision, the device needs to be unlocked first. However, we observe that users routinely unlock the device while charging. From this point on, a malicious charger could autonomously accept the input prompt. The bigger challenge for a malicious phone charger is the user consent prompt that ensures that the user intentionally takes the decision to enable MTP access. This mitigation builds on the fact that the malicious charger cannot trigger and accept the prompt at the same time. This is in principle ensured by the USB specification, which dictates that the USB board cannot act as a USB host and a USB device at the same time. However, in principle, we found multiple such possibilities on both Android and iOS. In the most intuitive attack, the malicious phone charger employs the combination of USB power delivered data wall swaps and a Bluetooth input device hidden inside our malicious charger. At the time of our research, this attack worked on both iOS and Android. First, a victim attaches its mobile phone to our malicious charger. Next, our malicious charger injects input events to start the Bluetooth scanning. This Bluetooth scanning makes the Bluetooth MAC address of the mobile device invisible. Then, in the fourth step, the Bluetooth input device, which is hidden in our malicious charger, initiates the Bluetooth input connection, which triggers the pairing request prompt. We use our malicious charger to inject again the input events to accept this prompt. So far, the malicious charger has been a USB device. Now, we inject a USB power delivery data wall swap that afterwards the device is instead of the USB host, a USB device. Sorry, instead of a USB device, a USB-C host. Then our malicious charger starts the MTP handshake, which again triggers the user confirmation prompt, and we use the Bluetooth input device to inject input events to accept this prompt. Lastly, our malicious charger retrieves stealthily the MTP files. Google assigned us a CVE for this attack and mitigated. Apple assigned us a CVE for this attack and mitigated it in the most recent iOS 18.4 update. Google acknowledged the attack and implemented some mitigations in the Android open source project. While this previous attack is relatively slow, a much faster attack is possible by exploiting a flaw in the Android's Open Accessory Protocol, or short AOAP. It allows a USB host to send special USB control requests that can inject input events. According to the AOAP specification, this only works while the Android device USB port is in a special accessory mode that does not allow concurrent MTP connections. However, we found this limitation can be bypassed. As a result, a malicious charger can simply initiate an MTP connection and use AOAP to confirm the user prompt it triggered. First, again, the victim connects its mobile device to our malicious charger. Next, we initiate an MTP connection, which then triggers the user confirmation prompt. We, as the malicious charger, injects input events through the AOAP to confirm this user prompt. And lastly, we again stealthily access files from the device. Crucially, we again disclose this vulnerability, and the Android patching is currently pending. In this demo, you can see this attack on a recent Samsung device. Pay close attention to the first few seconds. The user consent dialog is hardly visible before the attack confirms it. Did you see it? I will play it again. This short flickering is all you notice. From that point on, the malicious charger has access to all your files.
All right, let's jump into the second attack scenario. Now, we assume that the attacker has the victim device in physical possession, but the device is locked. In contrast to the previous scenario where we had the malicious charger, the attacker cannot rely on the user to unlock the phone at some point. Also, Android has disk encryption, so the unassuming user would think that files on the device are encrypted while the device is locked. However, this is not the case. Files are only encrypted after a reboot and until the user first enters the unlock pin or presents a fingerprint. So this is what the official Android documentation says about this. It says, if the user enables the lock screen after unlocking the device, credential encrypted storage remains available. And it's worth noting that credential encrypted storage is already the most secure storage class on Android. So for the attack, we simply assume that the user has unlocked the device at least once since the last reboot, which is a very reasonable assumption. Next, let me briefly introduce the basics of the media transfer protocol, or MTP. You can see that we have the USB host on the left and the mobile device on the right. Usually, the first thing that happens in the communication between those two is that the USB host queries for the mobile device's object handles, or also called file handles. And these are unique identifiers for every individual file that can be accessed on the mobile device. And you can see here that the mobile device responds with a list of these file handles, and then USB host can query for individual files properties or actual file contents. So you can see here that the mobile device responds with the actual file contents in response to this get object MTP request. Now, here is how the MTP protocol is implemented on Android. The part we'll concentrate on first is the MTP service. You can see on the right that the MTP service interacts with the functionFS Linux kernel driver to obtain MTP messages that arrive over the USB interface. And most of the actual MTP message handling is implemented in the MTP server class, right in the MTP service. And then there also is an MTP database class that contains a list of files to be served over MTP. Now, the USB manager system component starts the MTP service whenever the device is connected to a USB host. However, at this point, the MTP database is empty. And this is the reason why when you connect an Android device to a computer, initially you don't see any files on the device until the user confirms the user prompt. And now the USB manager maintains a field called mCurrentFunctions. And this field stores the currently enabled USB functions, such as, for example, MTP or USB tethering and others. And now when the user confirms the consent prompt actually calls to the USB manager. And you can see this call here. The method is called USB manager.setCurrentFunctions. And the value, the argument that is passed, represents the user's choice. For example, if the user chooses to enable MTP, then function MTP is passed as the argument to setCurrentFunctions. And inside the USB manager, this argument will eventually find its way to the mCurrentFunctions field. Now, it is crucial that whenever setCurrentFunctions is called, the MTP service is restarted, and this actually leads to the MTP database being populated if the current functions contain function MTP. And now here is how exactly that works. You can see that we have this excerpt from the MTP service. This is code that is actually executed when the MTP service is started. And now you can see that it queries the current functions from the USB manager. And if they contain function MTP, then only then actual storage volumes of the device are added to the MTP database. And inside the MTP database, you can see that we have this MTP storage manager class and the instance called mmanager. And this is where the volume is actually added. And inside the MTP storage manager is where the individual files are enumerated and assigned individual object handles or file handles. So these are, remember, these are these unique identifiers for every individual file. Yeah. So now at least this so far is how MTP is implemented in the upstream Android open source project. However, individual device manufacturers customize the MTP stack. They also customize the USB stack, but that is for another time. In the example here, you can see how one vendor modified the MTP database class. And the getObjectFilePath method that you see here is responsible for translating a file handle into an actual file path. And the part that is highlighted now is the implementation that comes from the upstream Android open source project. Usually, what happens is that the handle is passed on to the MTP storage manager, and the MTP storage manager, if actual volumes have been added to the MTP storage manager, will return the corresponding path. And then the result is transported to the calling layers. However, as you can see here, this also has a result when no volumes are added. It essentially returns null, and an error is returned to the upper layers. Now, you can see that the customizations of the vendor here add additional logic. And you can see that specifically for file handles that are above 10 million, the handle is taken as an identifier for a lookup into the media store. And the media store is a database of essentially all user files that are on the device. And now, crucially, this lookup does not depend on the MTP storage manager, which means that it works even while the user has not yet consented to the user prompt. And in fact, it even works while the device is still locked. Now, although the getObjectFilePath method shown on the previous slide is invoked from quite a number of different MTP message handlers, there are sanity checks in most places. You can see here, for example, the getObject MTP message handler calls to has storage before it actually processes the request. And you can see that if has storage returns false, this is the case if no storage volumes have been added to the MTP database yet. In this case, an error message is returned. However, we noted that there is no such sanity check for the doTruncateObject MTP message handler. And this leads to the following attack. It works on a locked device from Huawei, and we assume that the locked device is connected to a computer via USB. And now, for a range of file handles, starting from 10 million, the attacker carries out the following MTP communication. First, the attacker sends an MTP begin edit object message for the given file, or given file handle rather. And this on the Android device opens a file descriptor corresponding to the file at the path that is the result of getObject file path, the method that we saw earlier. Then the attacker sends an MTP truncate object message with the given file handle and size 0. And on the Android device, this will call ftruncate size 0 on the open file descriptor. And lastly, the attacker simply sends an MTP and edit object message, which closes the open file descriptor. And the result of this attack is that it effectively erases all user data from the device by truncating all files. So the list of files will still contain the same names, but all their contents will be erased from the device. We disclosed this vulnerability to the affected vendors who developed patches. Here you can see a demo video of the attack in action on an unpatched device. You can see that we start with a device where obviously there are images on the device. Now we lock the device, we connect it to our computer, and on the computer, we start the attack script. Okay, then we unlock the device again. You can see that it takes the unlock pin to actually get into the device. Then we refresh the view, and now all files are gone. And this is essentially because although the files are still there, they no longer contain any valid image information. So effectively, this erased all user data from this device, even though it was locked for the whole time. Okay, now let's dive deeper into the Android USB stack. We want to figure out if there is some way to exploit the USB manager state machine to get access to MTP, to the full MTP with all files while the device is locked. Remember that the USB manager maintains a field that stores the currently enabled USB functions, such as, for example, MTP or USB tethering. Now, whenever this field is changed, the set-enabled functions method inside the USB manager is executed. And you can see that this set-enabled functions method in turn calls the setUSBconfig method. And here, what is interesting is that a timeout handler is registered that fires after a delay of 3 seconds. And if the device is re-enumerated by the USB host before these 3 seconds, then the timeout handler is cancelled, so it's not executed. However, otherwise, the timeout triggers and the current USB functions are restored to a default state. This is what happens in this line here. And we now are interested in whether we can use this timeout, or this timeout handler rather, to enable the MTP USB function on a locked device just via USB communication. And for this, several conditions need to be met. First, we need to find a way to somehow invoke set-enabled functions with an argument other than function none. Otherwise, of course, as you can see here from the flow of the argument, the timeout handler does not actually reset the USB functions, and we want to actually trigger that logic. Second, screen unlocked functions, the default USB function, would need to be set to function MTP. So this is MTP mode, which of course we are aiming for. And then finally, we need to find a way to actually trigger the timeout. All right, let's talk about set enabled functions first. Again, it needs to be called with an argument other than function none. It turns out we can actually send the special USB control request for starting accessory mode. And you can see here, this is the logic that is actually executed if accessory mode is started. This is inside the USB manager, and you can see that start accessory mode actually calls set enabled functions with argument function accessory. And this is exactly what we are looking for. Now, this is not just what we are looking for in terms of the argument to the set enabled functions method, but this logic is even reachable on a locked device. So this is exactly what we need. Okay, we know how we can start the attack and force the argument to the correct value. Sorry. Now, what about mscreen unlock functions here? For the attack, we need this to be set to function MTP. And luckily, it turns out this is in fact the default USB configuration that can be configured by the user. So there is this option in the developer settings here where the user has the choice between several options. And file transfer, the first option here, actually stands for media transfer protocol. For MTP, this is what we are looking for. So we can assume that at least some users will already have this default USB configuration set to MTP. And crucially, even if the user has chosen to use file transfer as the default USB mode, it is only supposed, or file access is only supposed to be possible while the device is unlocked. You can see here, this is what the enlarged section of the screenshot says. It says, when another device is connected and your phone is unlocked, these settings will be applied. Okay, we have mscreen unlocked functions out of the way. We also know how to invoke the method with the right argument in the first place. So the only thing that is still missing is the timeout. How can we trigger the timeout? And it turns out this is actually pretty easy. We can just delay re-enumerating the device. In other words, we as the malicious USB host, we don't ask for the device's USB descriptors after putting it in accessory mode, after sending the special control message for enabling accessory mode. And this leads us to the following attack. Again, we assume that the device has been configured with MTP or file transfer, as it is called in the user interface, as the default USB configuration. With that in mind, the attacker can connect the locked device to their computer and send the special USB controller request for enabling accessory mode. In the Android device, this will switch the USB descriptor of the device, and the device will now await being re-enumerated by the USB host. However, we as a malicious USB host, we don't re-enumerate the device as it expects, but instead we wait until the timeout that we saw earlier kicks in. And we saw already that this will now reset the USB functions to MTP, the full MTP, where we have actual access to the disk contents of the device. And now this gives us 7 seconds until yet another timeout kicks in. And within this time window, we have, as mentioned, full MTP access. Now, this limited time window is not an issue at all, luckily, because first, the user, or the attacker rather, can simply repeat this procedure over and over. And second, there are MTP messages on Android that allow extraction of just chunks of individual files. So by repeating this process over and over, the attacker can essentially extract the entire file content or an entire disk contents of the mobile device. Of course, we responsibly disclosed this vulnerability with Google. They assigned us a CVE and rolled out a patch in the November 2024 Android Security Bulletin. You can see an attack or a video of this attack in action on Pixel 8 running the last Android 15 build that was still vulnerable to the attack. You can see that we start by taking a fresh picture on the device of this nice kangaroo in London. Then we lock the device. You can see that now it would require knowing the screen unlock pin to actually get into the device. We connect the locked device to the computer. You can see that the device remains locked for the entirety of the attack. Still, you can see that the attacker by now has extracted a list of files from the device and is now aiming to extract the actual file contents of the most recent file, which, as you can see here, succeeded. As mentioned already, we responsibly disclosed all vulnerabilities that we showed to the affected vendors. We are glad to report that they patched our attacks for the physical access scenario and for mitigating the malicious charger attacks. The first vendors are starting to revise their USB trust models. Android 15 and the most recent iOS 18.4 require user authentication before USB file access can be enabled. However, it remains unclear whether all Android manufacturers actually integrate these fixes, given the high degree of customizations that we already saw in earlier versions of Android across vendors. Recent Android and iOS versions also include so-called lockdown or restricted modes. And these are essentially improved lock screens, hardened lock screens that are supposed to entirely disable the USB hardware of the device. However, on Android, adoption of this feature is rather slow because this requires efforts from individual vendors to integrate these changes into their low-level USB stacks. And second, even these improved hardened lock screens are not immune to issues. For example, we found this CVE here that affects the iOS restricted mode. So even those improved modes can be bypassed in some cases. For end users, we have recommendations. First, always install operating system updates as soon as they become available. Second, bring your own power bank wherever you go, if possible. And if for some reason you still have to trust, or at least you have to use existing public charging infrastructure, then at least shut down your device so that you can take advantage of the file encryption capabilities of the operating system. This is particularly critical for Android devices. To conclude, here are the key takeaways for our presentation. First, ChoiceJacking style attacks where malicious chargers extract files over USB are still possible against popular belief. We call these attacks, these improved attacks, ChoiceJacking attacks, because they can bypass user prompts to extract files over USB. Second, file extraction is even still possible on locked devices and even on state-of-the-art devices and operating system versions. And lastly, we recommend to watch your phone. Don't hand it to any strangers and only use trusted chargers. Thank you very much for your attention, and we are happy to take your questions now. If anyone has questions, please ask them at the microphone stands. Yeah. Could you maybe ask it into the microphone so that it's recorded as well?
Hello. So about the Huawei device, how did you pick the specific model on which to test your ideas? Why Huawei? Why this specific model?
It's basically random choice. Basically, we had constraints in terms of money, of course, and constraints in terms of availability, because we are from Europe, where only a small subset of devices is actually available.
All right, thank you.
Yeah, but still, we assume that the attack, I mean, now it's fixed, but back when we found it, we assumed that the same logic could be found in basically all devices from that manufacturer. Hello.
On your second on Android with USB, you using it USB debugging mode?
You mean ADB mode or
ADB mode.
USB debugging? No, that is not involved at all. We're only using MTP, the MTP protocol. Yeah.
How you think can you trust USB debugging mode like USB MTP request?
Well, in principle, file extraction is also possible over ADB.
Yes.
But it requires that the device has been development enabled, which we sort of implicitly assume for the last attack that we showed, but we don't in general assume that. So most of the attacks work on completely stock devices that are not development enabled.
Thank you.
Yep, you're welcome.
Hello.
Hi.
I just want to ask, like, you know, some countries do have renting out the portable charger as a service. So people just rent the portable charger from the street, right? So is it easy to like have this kind of attack, like public charger become a malicious charger?
I'm not so sure whether the question is how easy it is, but it certainly is possible. Technically, there is nothing that prevents an attacker from miniaturizing the attack or even probably implemented on some small scale platform that already exists and implanted into some existing charging product. Any more questions? Doesn't? Oh yeah.
Thank you for the talk. I'm sorry I was a bit late for the beginning, but can you clarify? You focused only on Android. Is there anything similar for iOS?
We had two parts in the presentation. The first part was about more generic attacks that exploited the trust model of USB in mobile phones in general. And one of the attacks there actually did affect iOS as well. I guess we have...
When you can attach like a virtual keyboard and interact with the device?
Yeah, it's a combination of that and several additional mechanisms like USB power delivery, data roll swaps, and Bluetooth input devices.
But the CVEs you submitted were all Android, right?
No, we did receive a CVE for iOS.
iOS as well.
Yeah.
Okay. Okay, cool. Are you planning to publish this, or is it publicly available?
We will publish the details at Usenix Security. So we have a paper at Usenix Security.
Excellent. When is that?
Sorry?
When is that?
In August.
Okay,
this year.
Thank you very much.
You're welcome. Do we have any more questions? Otherwise, then of course we are still here to, so you can approach us after the talk. With that, thank you very much for your attention, and hopefully see some of you later on.